Howdy, y'all. Is there a handheld microphone, or can you all hear me? Yep. All right, cool. So my name is Travis Goodspeed. I got drunk with some friends one night and came up with the idea for the Southern Appalachian Space Agency. So I bought a satellite dish, and I bought a motor to control it, and that became the first ground site. Using this, I scanned some television satellites, and you can get data from them, and I had all sorts of fun with that, but it wasn't really anything new because Adam Laurie had already done it. So this lecture is about the second ground site of the Southern Appalachian Space Agency. This is in East Tennessee in the southeast United States. And I basically bought a satellite dish from a United States Navy warship, and I replaced all of the electronics in it to have my own targeting computer. And then I wrote Unix daemons that would target different satellites in the sky as they were moving. So unlike a TV satellite dish, this dish can actually track moving targets. I can track targets in Earth orbit. I can track targets in solar orbit, so like spacecraft and that sort of stuff. I can track Voyager 1 and Voyager 2. I can also use it as a radio telescope to measure the redshift on the hydrogen line of stars in outer space. A friend of mine blackmailed me into including a picture of a dinosaur rock band. A lot of this work came about because some friends of mine in Berlin, SkyT and Fabs, were friendly enough to give me a quiet place to work on it. And also, thanks are due to Adam Laurie and to Jim Giovetti for the satellite research that preceded mine. And to the Scooby crew at Dartmouth College. It's a professor named Sergei Bratis and some of his students who do very good work and inspired a lot of this research. This is the logo for the Southern Appalachian Space Agency. And I'd like to explain the different pieces of the logo so that you can appreciate my people's native culture. In the middle is the satellite dish, and you'll notice that it's on cinder blocks. It's traditional where I come from to take a car. Maybe you've got a lot of cars, but you don't really have any money, so you need the wheels from the car to put on another car. So you just sort of take them off and leave the old car on cinder blocks in your front yard. This actually is the way that the dish works, and we do have it sitting on cinder blocks. On the left, you'll see a farmer with a shotgun. And the reason why he has a shotgun is because of the alien on the right. You might call him E.T., but we call them boogers. They're like little green men. They're this tall. And the farmer has the shotgun so he doesn't get abducted. In the sky, you can see the International Space Station. But there's also a banana peel and a bolt and a glove. And this is to represent space trash. In the back right, just above and to the left of the alien's head, you'll see a moonshine still. We make our own whiskey out of corn, out of maize. And so I tried to represent all of my people's traditions here. Now, it looks like the mountains have snow on the top, but our mountains are not that tall. It's actually that we blow up our mountains for strip mines. So at Berlin Sides last year, I gave a talk on reverse engineering the Spot Connect. This is a Bluetooth to satellite transmitter that's intended for people who do hiking. So if you're going hiking in the middle of the forest somewhere, there's no cell phone reception. So if you get in trouble, or if you need to tell your mother that you didn't die in a horrible accident, you can't use a cell phone, and satellite phones are very expensive. The Spot Connect is sort of a one-way pager. So you can't receive any messages through it, but you can transmit messages. This goes to a server that they control, which then gets sent over the internet. So you can tweet through this, you can send text messages, you can send emails through this. Very short ones, but I wanted to be able to sniff this. So I took a software-defined radio, and I recorded the uplink, which is at 1.6125 gigahertz, and it's clear text. It's completely unencrypted. You just need to figure out how to decode it. It contains the serial number, the GPS coordinates, and the text that you're sending in your transmission. This is a picture of the device. It's just like a little hockey puck size device that connects to your phone by Bluetooth, and your phone is the only interface to it. There's also an emergency button so that you can call for help if you need it. On the left is the Android application that controls this device. On the right is the result of the email that comes out of the device. So I said that I was walking west. I was at 38 degrees north and negative 75 degrees west. And this is in Philadelphia, crossing the Schuylkill River. But this goes through a satellite. There's no actual cell phone connection that does it. Even though my cell phone does have service in this picture, it works just as well with no service. Among the reverse engineering that I did of this device, I figured out how it worked at the PHY layer. This is a diagram that shows you how to read the signal. Basically, it switches between two different random number sequences. And so it sends a long stretch of one sequence for a 0, or it might be a different sequence. And the transition between them causes a little pop on the receiver. So wherever you see a pop, that means that it used to be a 0 and now it's a 1, or it went from a 1 back to a 0. And you can write a program that decodes this. The trouble is that sniffing the uplinks isn't very useful because you need to be near the transmitter. So if we're on a hiking trip together, it's easy for me to see that you're sending a message, help, help, I'm with this crazy guy. But it's not enough for me to get them out of the sky because you need a satellite dish. And it has to be a satellite dish that can follow moving targets, because this device transmits to satellites that are very low above the Earth, in low Earth orbit. So a geostationary dish, the sort that you would use for TV, is not enough. So the TV work, I'll get back to the spot in a minute, but the TV work that Adam Laurie published in 2008 and 2010 used a KU band satellite dish. These are the 1 meter dishes, not the 3 meter dishes. He had a DVB-S satellite TV receiver card, and then he ran Linux. And there's actually a standard for controlling a motor that will move left and right. So there's an IOCTL call that you can run from Linux to actually move the motor left and right. And he published the code for that at SatMap on his website. And he wrote a feed scanner tool that runs through, and after you guess the angle at which the satellite is, you can then run through and try every frequency. When I was figuring out how his work worked, I built the same system myself. And in this graph, the x-axis at the bottom, that shows the angle that the satellite dish is turned to. And the y-axis is the frequency that the frequencies are on, the frequency that the transmissions are on. So you can see that there are 4 or 5 different satellites in view. You'll also note that the ones that are next to each other try not to transmit on the same frequencies. This is so that they don't interfere with each other. Now, the advantages of this are that working with the TV satellites is very cheap and very easy. You can buy, you can find an old dish that people throw away. You can get a DVB-S card at a flea market. I got one in Berlin at Mauer Park for €3. And then you just plug them together, and there are standard Linux drivers, and you can write standard Linux software to receive it. And you get these TV signals with video feeds. So sometimes you can watch people being interviewed. Like on the news shows, when they interview subjects, they bounce it through this network, and you can watch these interviews live. There was also a case a few years back where several of the drones were actually sending their video feeds over this network. And people were recording videos of military drones flying over countries in the Middle East, because this was being sent in clear text over just a random unused channel on a TV satellite. But there are disadvantages to this. It only works on geostationary satellites. So it only works on satellites that orbit the Earth just as fast as the Earth turns around, because those satellites stay in the same piece of the sky. There's also no elevation control. So if you look at the southern sky, there's actually a belt in the sky called the Clark Belt, which is where all of these satellites are. But because you can only move left and right, it's hard for you to target things that are very far from each other. So you have a slim window of the sky that you can work with. It's also limited to standard signals. You can get video and you can get TCP/IP data, but you don't really get mobile data. You don't get animal tracking bracelets. You don't get ship tracking. You don't get telephone calls. You don't get anything weird. And I wanted to get the weird stuff. So I bought a dish. This is my dish being removed from a warship. In the States, because we have like such a large country and such a large military, the military throws stuff away. And they have these Army-Navy surplus stores, which is where you go if you want to like get a pair of good boots or something. But you can also buy satellite dishes from them. So I bought one. It's a Felcom 81 dish. This was intended for use with Inmarsat. Inmarsat is a satellite telephone network. On Inmarsat, this dish would sit above the ship on the top of the mast, and it would aim at a stationary Inmarsat satellite. And then it would get telephone calls routed through it. It's 1 meter in diameter. It has stepper motors for azimuth, which is turning left and right, and elevation, which is turning up and down, and tilt, so you can actually tilt the dish so that moving up and down will follow the curve through the sky of a satellite. It has mechanical spinning gyroscopes, because keep in mind, the target that this was originally designed for stays still in the sky. If someone could get me a water. Yeah, fuck it. Glass? So this was designed to sit on the top of a moving ship, and the top of the mast on a ship moves the most. So it's being jerked left and right. The ship itself might be turning, and then at the same time you have the whole ship rocking from the ocean. So it has motors and it has gyroscopes, and the software that originally ran on this dish would just try to keep the dish still as the ground beneath it moved. So the ship moves, the satellite dish stays still. If you've ever seen like one of those rocket launcher trucks that's driving down the road, where the rocket stays still while the truck itself is bouncing every which way, it's the same technology. And this is very easy to do because you can do it with a mechanical gyroscope. But nowadays we have MEMS gyroscopes intended for cell phones, and they're really cheap. And stepper motor controllers are very cheap as well because they're used in 3D printers. So I bought this dish for $250 on eBay. It was another $200 to have it delivered. If you want it to be sent by air, you're going to have to pay a fortune. So if you'd like to repeat this work, I recommend that you get it locally. And then I wrote my own software to control this dish. Now I wanted to track satellites in low Earth orbit. So what I did was I had a daemon written in Python that predicts where all of the satellites will be. I have another daemon that controls where the dish is aimed. And then I run these, and they all communicate through a single Postgres database. If you were able to get a SQL injection vulnerability against this server, you could inject a command to move the dish. I also use a software-defined radio, and this allows me to take a recording now and then figure out which signal I want to tune into later. So if I'm not quite sure exactly what the Doppler shift will be, or I'm not quite sure exactly how to interpret the signal, I can take the recording first and then later reverse engineer how to decode it. Because what I really want to do is to document the undocumented downlinks. I want to be able to find the signals in the sky that nobody knows about. So the whole thing is built as a series of Python daemons. I have a BeagleBone, which is a small ARM board that runs inside of the radome. That's the fiberglass cover that goes on top of the dish. And then I have an x86 server that's inside of the house. These two are connected by Ethernet. And I use Postgres for coordination. So if you want to know where the dish is, you can run select azimuth and elevation from position. And bam, you get like a single row that shows your azimuth and your elevation. If you want to target something in particular, you can update the name column of the targeting table. So you say update target, set name equals Voyager 1. And from then on, it will begin moving its position to track Voyager 1 as it goes through the sky. I use Realtek software-defined radio for the software-defined radio. You can buy these for €20. And then there's just a bit of software on the BeagleBone that grabs the radio samples over USB and then sends them out over Ethernet to my server in the house. So I can have a very powerful server without having to put that server in the yard where it might be rained on or things like that. And then I have an iBot board to control the motors. And I have a vector nav inertial measurement unit to measure by acceleration what my elevation is. And it also gives me a guess at my azimuth. This is a close-up picture of the dish, the friend of mine working on it. This little spiral thing on the right is an L-band antenna. And the nifty thing here is that it can both receive and transmit. The silver box that's right about there, that silver box is a 200-watt transmitter. At the moment, I have the transmitter removed for safety reasons, but if I reconnect it, I can microwave squirrels by targeting them with this dish. In America, there are lots of rules from the federal government about what channels we're allowed to transmit on. However, in Tennessee, we have a different constitution. And in Tennessee, in 2010, we changed our constitution. As a Tennessean, I now have the right to hunt and to fish. So if I use my dish to hunt squirrels, I think that's constitutionally protected. Does it show that I'm not a lawyer? This is the rear of the dish. This white thing on the bottom left, that is a power strip. So I actually run AC electricity into the radome. And then I just plug the different devices into that. Our initial design involved running DC in, but it became too difficult to perform maintenance. And then all of the equipment is actually strapped onto the column of this dish, because the entire column has to move left and right, and it has to be balanced, or else the column will lean, and that makes the targeting more complicated. And you can also tell by these photos that Tennessee is a very rural place, because all of these tires in the background are what used to be on the cars, and that's why the cars are on the cinder blocks. So strapped onto the column of the dish, this is just a powered USB hub on the right, the green board. The white board is the BeagleBone, and that's the ARM CPU that runs the dish. I actually SSH into that board and then start up the Python daemons in order to control the motors and to send the radio data back. The red board on the right is the motor controller to control the stepper motors. Stepper motors only come in a couple of different styles. So it's very easy to figure out how to move the motor in one direction or another. And you give it an integer number of steps, and by measuring how many steps there are in a full circle, and then dividing by that, you can figure out exactly where you are by dead reckoning. But you're measuring like how the joint moves, and the contraption might tilt, or you might jump off by a step. So this is why I have the inertial measurement unit to measure gravity in order to know what my elevation is as a sort of second backup measurement. This is the iBot board, which I use to control the motors. You might remember this from another project. It actually comes from the EggBot printer. So this is a printer that uses a pen to draw on Easter eggs for children. The same motor controller works on my satellite dish, and it works perfectly. It never misses a step. I also have a camera on the back. This is a webcam that sits on the back of the dish pointing outward. Now, when the dish actually has its lid on, it just looks like this bubble. The bubble is called a radome. This is the inside of the radome with my cat Frank. So we painted it. And this way, if I forget where the dish is pointing, I can figure it out by looking through the webcam and seeing what number of the clock I see. So if I see 12 o'clock, I know that I'm pointed south because the camera points backward from the dish. The reason why I have these things is that this dish is in Tennessee, and today I'm in Serbia, but when I did a lot of this work, it was remotely from Germany. I would SSH into Tennessee and then write the software to run on the physical hardware. And it's a lot of work to call my father and my brother and say, hey, can the two of you go out and tell me which angle it's pointed at? Find a compass. This is a screenshot of the software that I used to target it. All of the control software was first written blind without any GUI. I actually had a SQL terminal open, and I would do SQL queries to figure out where it thought it was pointed, and then I would either travel to Tennessee to look where it was pointed, or I would look through the radio. I began to navigate around local FM radio stations because I could aim the dish at them, and when the signal strength got really loud, then I knew that I was pointed in the direction of the tower. But this software was written later on, and I needed a GUI in order to demonstrate this, and I needed it the next day. The advantage of having all of this run through Postgres is that I can just use the Python PostgreSQL library to throw together a GUI in a couple of hours. So I hacked this together with Python and Pygame, which is intended for children to learn how to make their first 2D video games. In this case, the satellite dish is pointed at GOES 3, and it's on target, so all of the numbers at the top are green. I can also show stars, so these white... Can we dim the forward lights just a bit? Maybe not. So all of these white markings are stars that are in the sky. So if you're actually out and looking at the night sky and you're trying to see where something is pointed, this gives you a map of where the stars are that you need to look at in order to know physically where the satellite that you're targeting is. There's also a polar view. So this makes a little bit more sense in that you can see that it's pointing south and just a little bit to the east. And Polaris right there, just north in the dead center of the polar plot, and just above the green line, that's the North Star. As you watch this through the day, you'll actually see all of the stars rotate around the North Star, which is caused by the Earth spinning. So, and a particularly strange piece of this was that I was seeing the stars both from the wrong continent, and I was seeing them during the day, which completely ruined any hope of my learning astronomy. Now, the other advantage of this being in Pygame is that you can run it on a cell phone. So this is my Nokia N900 running the exact same software that my desktop runs. The Postgres is running through an SSH tunnel, and this is running over 3G through Vodafone. So I was actually able to develop this while on public transportation in Berlin. I would sit on the metro and I SSH'd into Tennessee, editing the source code and displaying it. It also runs on more modern cell phones. This is a Nokia N9. I think you might be able to kludge it up through Android. But you could also just rewrite this, because the GUI part of this is very small. The GUI knows nothing about satellites. It knows nothing about what's in the sky. All it knows is the results of SQL select statements. And the only output that it does is a SQL update statement when I click on a satellite that I wish to target. This is some of the software that I use for viewing the results. In this case, I was trying to identify where a couple of very loud satellites were in the sky. These were weather satellites. So I set the radio to record on a frequency that I knew was in use by the satellite. And then I had it dump its output into that same SQL database. Hundreds of thousands of rows, but the server can handle it. You know, it's a lot smaller database than the one that Facebook keeps of all of your private information. And I then loaded it into a program called Viewpoints, which NASA publishes to help with physics experiments. The idea is that you give it a scatter plot in many dimensions, and then each view is choosing some 2 dimensions. So the top right view shows the signal strength per angle of elevation. The bottom left shows the azimuth and elevation. So the bottom left is the same thing that you see on the operator's console of SASA Commander. And then the bottom right shows the received signal strength with regard to the frequency. So I can see that in the bottom left that there are 2 different channels being used for transmissions. From the top right, I can figure out exactly which height in the sky the satellite is at. And in the bottom left, I've highlighted what I believe are 3 different satellites and their positions. So using this sort of view, you can work backward from your view of the sky to try and figure out where the satellites are. Now, each one of these runs as a different daemon, so if there's a serious bug in any of them, I can rewrite it from scratch. There's one daemon that does orbit predictions. The first time I wrote this, it was very ugly, so I threw it away and I rewrote it. The second talks to NORAD and downloads a list of the 2-line elements that describe the orbits that the satellites are in. During the Cold War, there were worries about intercontinental ballistic missiles. These missiles look just like satellites, and in a way they are, because it's just a missile that's fired out of the atmosphere and then it re-enters. So all of the missile defense systems occasionally get false positives for satellites. So NORAD publishes a list of all of the real satellites so that if you see something in the sky, you can know what it is and not freak out if it's something benign. But I can download that same database, and that tells me where everything is in the sky in order to target it. This is how I know where the different satellites are. And I have a daemon that connects to a server for this, grabs these satellite positions, and loads them into my database every night at midnight. I also have a daemon that controls the motors. I have a daemon that measures the accelerometer readings. And I have a couple of different radio daemons depending upon whether I'm close or far away from the radio, whether I want to use it live or take recordings to read later. My hope is that later in this project, I can publish a 1 terabyte hard disk image that contains recordings from several different satellites for radio experimenters to play with without having to have their own hardware. For my first orbit predictor, I used a program called Predict. This works rather well, but it's terribly old. I think it was first written for DOS and later ported to Unix. And you actually make requests from this program by UDP while it's showing you the results on a GUI. My problem with this was that it could only do 20 different satellites at a time, and I needed a lot more. So I switched to a library called PyFM, which supports hundreds of satellites, and it does not require any UDP connections, and because it's a library, you can do performance hacks on it. It calculates not only satellites, but also planets, so I can ask it where in the sky Mars will be, and it tells me exactly where to aim to view Mars, or the stars. It can track up to even more than 500 targets without difficulty. This is a screenshot in which I'm tracking every single satellite in geostationary orbit. This is called the Clark belt, and you can actually see the belt through the sky. These are all of the satellites that are at the same height, because your orbital speed is determined by your altitude. So they're all at the same altitude, and they're all in different positions, and I just see them as a ring. These two-line elements are freely available from celistrack.com. So you can download all of these entries and then plug them into the PyFM library and predict where these things will be in the sky. And then the prediction daemon just selects these after they've been inserted into the database. So by doing all of my inter-process communication through Postgres, if I ever run out of server strength, I can just add more servers and move the daemons away from each other. At present, I have 2 machines, but later on I could go to a dozen or more. The motor control daemon takes stepper motor commands. It just appears as a serial port, /dev/tty/acm0, and the baud rate doesn't matter because this is a USB serial port. If you want to move, let's say I want to move 500 steps upward, and I want to move 400 steps to the left, and I want to do this over 3 seconds, I just run sm, 3000, 500, -400, and I send a carriage return, and it does it. And when it's done, it says OK. So it's just as easy as talking to an old modem. There are similar commands to disable the motors if I want to be able to freely push the dish around, or to change the step size so that I can move a fraction of a step if I need very precise aim. And all we did was cut the motors off of their original control boards and wire them into our own. So we didn't have to do very much reverse engineering of the existing control software. We would have reverse engineered it if we thought it would be valuable, but it's only useful for tracking a stationary target from a moving platform, and we needed to track moving targets from a stationary platform. The stepper motors have part numbers. If you call the supplier, they will not answer the phone or reply to your emails, but it just has 6 wires, and you only need to know to take the outer 2. We then wrapped these cables in wire wrap, and we tied them in place with zip ties. It looks ugly, but it's held steady, and we've had months of uptime without any physical issues. Now the accelerometer is a Vector Nav 100. This is a MEMS gyroscope, and also an accelerometer, and also a compass. So it can actually tell within 2 degrees where the device is aimed in azimuth, and within maybe half of a degree in elevation. We need targeting of better accuracy than that. So instead of using this device to actually target the dish, we use it to sanity check. If the motor ever gets stuck, then this device will tell us where we really are, even though our guess at where we should be would be completely wrong. And by comparing the two, we can recognize in software whenever we've hit something. And this is how the dish knows to shut itself down rather than tear itself apart or aim at the wrong place in the sky. There are all sorts of bugs in the inertial measurement unit. So at the moment, we're ignoring azimuth and only accepting its view of elevation. And the tilt motor is currently unused. So even though our device is physically capable of leaning left and right, we don't yet have the software to do that. So we just leave that motor locked in place. The radio daemons act as either a spectrum analyzer to identify which frequencies are in use, or a downlink recorder, which actually records all of the raw samples as a software-defined radio and saves them over NFS, the network file system. By doing this, our tiny little computer inside of the radome has access to the massive hard disks of our server inside of the house. And this way, there's no worries about the speed of flash memory or the physical stress of a disk being moved around. It just all happens over the network, and upgrades are no problem, and we don't have to worry about the weight. So you can actually create a SQL query that says, what is the strongest signal in the sky at roughly 6 degrees up and 3 degrees to the right at June 21st at 3 p.m. And then it'll run through the database and grab that position at that time. This is useful when you're trying to track a moving target. So if a satellite is moving and you don't quite know what one it is, well, you can combine your observations of it to later search through the orbit databases. We can also dump these as text files, which we can then load into other software like MATLAB or Viewpoints. Viewpoints is amazing. It's this scatter plot viewing tool written in OpenGL. And the idea is that you take all of the raw data and then you start annotating it by what you see in different two-dimensional views. So for example, if we look at the time and the frequency, we can see the Doppler shift. When you have a radio that's receiving a signal from a moving target, there's actually a Doppler shift that shows you how fast that satellite is moving in relation to yourself. Just like an ambulance's sound changes as it passes you on the street. So by measuring this, we can actually figure out where the zero crossing is, because the frequency first gets higher as it's approaching you, and then it gets lower as it goes away. So if you can find the center frequency, you can figure out when it came closest to you, and that helps you identify what object you're looking at. By looking at azimuth and elevation, you can sort of see a view of the sky and find physical positions and also orbit traces. You can also look to see a traditional spectrum print by looking at the RSSI, that's the received signal strength, and comparing that to the frequency. The Pygame is written the client GUI is written in Pygame because this works on everything. It's a very lightweight library. It's intended for children to make video games. But it's very easy to draw pixels on the screen, and it's very portable, so it runs perfectly on my Nokia phones. And again, we're just using Postgres for communication. So you can do a select statement to read data out of the database and an update statement to order a different daemon to do something else. And the server does all of the heavy lifting, so none of the important number crunching is done inside of the radome. And in this light you can't see it, but this is actually showing some of the received signal strength traces, and there are blue lines in this picture which show the traces, the path through the sky that individual objects took. Could we turn off the lights for just 1 second? Getting closer? Okay, so you can sort of see them on the top right where they're brightest. These blue lines are the orbit traces of moving satellites as the receiver followed them through the sky. So today we have accurate tracking of satellites. This can run, we can turn the lights up a bit now. This can run for 24 hours a day for months of uptime. Because this runs through daemons without the need for a direct operator, This can run at night. This can run while I'm sleeping or while I'm eating or while I'm doing other things. And there's a daemon that just records all of the radio data to be read later. So as soon as I add more storage, I can begin collecting a database. So the next step is to port scan the entire sky. I can't get the whole sky. Like, I can't see the TV dishes that you see, the TV transmissions that you see from Serbia because the Earth is in the way. But I can see everything that goes through the sky in Tennessee. I can also see every downlink that fits my antenna. So I'm sort of limited by my antenna to between 1.5 and 2 gigahertz. But I can later add more dishes to do different frequencies. And I have a big yard. I have land is cheap in Tennessee, so it's very easy to have a lot of these different dishes. I'm hoping to get, say, 10 of them and run them all with different size antennas, and then to produce a sort of 1 terabyte hard disk with recordings from everything, so that you can, by software, play with things that are in the sky and begin to interpret unknown signals. There are other ways of tracking satellites. This is a photograph of a ham radio receiver that moves in azimuth and elevation. This can receive pictures from weather satellites, and this can receive audio from ham radio satellites. There's a bulletin board system on the International Space Station that you can use to send email, not through the internet, but just through itself. So if you wanted to send a message from Serbia to Tennessee, you just wait for the ISS to come through your sky, you upload your message to it, and then later when it's over Tennessee, I could download the message. I was told that you should end every lecture with a cat picture. So this is my cat, Frank. We didn't know it at the time, but she was pregnant. And if any of you would like kittens, I would be happy to give them. Thank you kindly. How am I on time? Do we have time for questions? Yeah. So do you have any questions? Yes.
Where did you get those ideas?
A friend and I enjoy a scotch called Lefroy, and we drink it and we come up with crazy things, usually from watching bad hacker movies. Like, you know, in the movie where the telephone networks go out and the guy just has to hack into a satellite, and he's like, oh yeah, I'll just put this thing on the roof and I'll do it. Well, how reasonable is that? And it turns out, like, while it's not as easy as it is in the movie, you can do a lot of things that they do in the movies. It's not as absurd as it sounds. Yes?
So, what happens when you turn on the...
Wait for the microphone.
So could you just kind of elaborate on what happens when you turn on the 200-watt transmitter and point it at, let's say, a random satellite up there?
So I've never turned it on with the antenna connected. I imagine that it would involve black helicopters. But I would feel very bad if I accidentally broke a satellite or something like that. The 200-watt transmitter would not be strong enough to hurt the satellite, but it would be strong enough to jam other signals. And there have been cases in history where satellite communications were jammed or replaced. There's a man who is angry at an American satellite TV company called DirecTV. So he used a satellite dish to hijack their video feed to inject text saying that they were assholes and that their customers should switch to their competitor. Yes? It's hard for me to hear. If you could pass the microphone his way, or if you could yell.
Are you planning on developing some data mining software for that raw data that you have been recording?
My plan is to build such tools in an ugly way for my own use. I might share that code, but I'm hoping that someone who is better with radio software builds the tools to data mine the database after I publish a copy of the database.
So you're planning only just to publish the raw data, and we could just data mine some useful information from that?
Yes.
Okay.
Yeah. Finding simple data out of the database is rather easy. You can come up with select statements that kind of work. But it really takes a lot of patience and a lot of signal processing knowledge to get more out of the database. And that's why I intend to publish, if not all of it, at least a terabyte of it.
You said there were libraries of every satellite in the sky, in order not to confuse them with missiles. So have you ever observed anything that wasn't in the libraries?
I don't know. I don't think so. Part of these libraries is that suppose that you wanted to hide a spy satellite, it would be more conspicuous if it weren't in the database than if it were, say, mislabeled. So I expect that by looking at the database, you can measure how often rocks change to find the difference between, say, an old broken satellite and something that's still flying and still using rockets. You could also do this to measure the mass of something, because as a satellite flies low to the Earth, there's just a little bit of air, and that causes air resistance. Small objects fall faster because they have less mass to keep their speed up. Data mining that database would be very interesting to see. And it's available through celestrac.com if you'd like to play with it. Yep.
I'm sorry. Your antenna seems to be. It seems to depend on the direction of the dish. In order to send and receive any signals, it has to pick a target with great precision. And what about the other way around, from the sky to us? Is it not logical to expect that most satellites have emitting dishes that are not pointing at the Tennessee, but to some specific targets, so that you cannot see them actually? Or am I wrong about this?
You're correct, mostly for imaging satellites. So if the other thing that would make a spy satellite hard to see, or even just a weather satellite that needs a lot of bandwidth, is that they will use a spot beam to a given ground station. These are usually done where they know exactly where the receiver will be. So for example, some of the weather satellites will aim toward a particular ground station in Alaska. And as they fly over Alaska, they aim a dish at the ground station and they transmit just at that ground station, and you need to be within a few degrees of that ground station in order to receive it. So the third ground site, I bought a TV news van in Chicago, which can be driven to different cities. It's a long drive from Tennessee to Alaska, but if you know the ground site of the satellite, and very often this is published, you can actually just move a satellite dish to that city. And because their spot beam, I mean, even though it's small, it's still a couple of degrees, like 2.5, which means that it will necessarily leak outside of the fence line of the legitimate receiver. So yes, you're entirely right that that happens, but you can work around it.
Thanks.
Yes. I'm going to stop pointing at people. He's now in charge of who does the next question.
Yeah, sorry. So if your antenna is aimed at a particular satellite and you start recording the signal, I know that you mentioned the television satellites and then not television satellites. I got confused here maybe. But if I'm recording for one television satellite, I have few full HD streams of video coming from that satellite, right? I can have dozens of them. And that's a crazy amount of bandwidth. And if you record everything that satellite transmits, I'm just interested what's the bandwidth of the data that you are writing to your hard drives, and how is it possible?
So the bandwidth is limited by the radio, not by the transmitter. So in the case of television satellites, my present receiver, first of all, I'm receiving at, say, 1 to 2 gigahertz. Television satellites transmit at 12 or 13 gigahertz. So I can't get TV signals with this dish because my receiving frequency is so completely wrong that I can't work around it. The second problem that you mentioned was the bandwidth. If a TV satellite, or let's say a weather satellite, since that's something I can aim at, a weather satellite sends a very narrow picture for amateur people to receive, and it sends a very high resolution picture for weather stations to receive. For the high resolution pictures, generally I get like some lump of spectrum. I believe my current station gets 3 megahertz wide, and as soon as I upgrade the radio, I will get 20 megahertz wide. So at the moment, my receiver isn't wide enough to get more than, say, 1 television channel. Later on, I will be able to get a few of them, but I still won't be able to get everything that the satellite is transmitting. So I have to pick first a position in space, and then a position in time, and then a position in frequency, and then I have to figure out how wide a recording I want to make. And then I fill up my hard disks very quickly. So the amount of data is definitely a problem, but it's a manageable one as long as you're willing to maybe only get a couple of channels at once. This is a bad choice for pirating satellite TV. I'll switch to the good stuff.
Moving away from technical stuff, I want to ask you, you've been testing this while you've been developing and making all this stuff. What's the weirdest and funniest thing you've caught on radio while doing this?
I heard God. And it turns out that it's not that I found the coordinates of heaven. It's that a local Christian AM radio station was transmitting with illegal power. And it was running through the, like it's a small village, right? So the Christian radio station is on one side of town and I'm on the other side of town, but there's a clear line of sight between us. And so I was listening to this recording of what should have been a data signal from a satellite, but the satellite wasn't transmitting. So I turned up the amplifier and I turned up the amplifier, and then I just heard this voice and it said, "It takes a holy light and it takes dedication, and it's not..." And, you know, I was wondering what was going on until I took another recording and it said, "You are listening to WJFC, bringing you 24 hours of quality Christian talk radio."
So
there are some satellites in the sky that failed in like the 1980s. And then eventually enough radiation hit them that they got fixed. Say the batteries in one broke, and it just disappeared for 20 years. No one knew where it was in the sky. Everybody thought it was broken. And then one ham radio operator was listening and he heard Morse code on a channel that no one should be using. And it was the call sign of that satellite after it woke up from the solar panels being repaired. There's all sorts of crazy stuff up there. Especially because when you launch a satellite, if it breaks, you're supposed to crash land it, but only if you can crash land it into the Pacific Ocean without hitting anybody. And it's a lot easier to say that's kind of hard and just push it up a little bit. And these things are still floating around up there, and sometimes they break, but sometimes they hang around. Very often the transmitters will be turned off, but if you can get the command books for them, you can actually turn the transmitters back on. If you happen to find any of these books, please hook me up.
So about the storage problem for storing all this data, have you considered using the archive.org? I think they're interested in historic documents and mostly, video recordings, audio clips.
I have thought about that, but I have another issue, which is that my village is very small, and it's not exactly up to modern times. We legalized alcohol 5 years ago. We briefly had a bar. We don't have the fastest internet access. So when I bought this TV news van, which by the way has a 20-meter tower, a microwave tower that comes out of it, it has an air-conditioned office in the back. They canceled the model because it was too large for the American market. It has a 10-cylinder engine. And in the back, because this was used by the TV news, there are 3 19-inch server racks with their own air conditioner, which means that I can just fill it with rack-mounted solid-state servers, flush all of the data into the van by gigabit Ethernet, and then, when I've filled it, I can get in the van, disconnect the Ethernet cable, and drive to the Internet Archive.
Don't underestimate the bandwidth of a truck full of tapes. That one.
Exactly.
Another question though, the gyroscopes that you mentioned, did you do anything with it, or were the cinder blocks actually a good replacement for them?
So the gyroscopes themselves are mechanical. Keep in mind that this dish was manufactured in 1997, so they had no MEMS accelerometers at the time. And back then it was actually controlled munitions to have an inertial measurement unit. Because the only use for them, I mean, we're talking like big boxes like this, they were only used for missiles. You couldn't fit one in a cell phone. But then the iPhone came out, and suddenly the chips are cheap as dirt, and you can buy them for $1. So I wound up just ignoring the existing gyroscopes because they only give feedback in the form of like too far forward or too far back. So it's only a little bit of output, and it wouldn't tell me where I was, and it wouldn't tell me how far I had moved. It's only useful for staying still. At the same time, a friend of mine wanted the gyroscopes because before he defected from the Soviet Union, he worked on missiles, and he thought it'd be cool to have like the old gyroscopes that they used. Unfortunately, the entire satellite dish is balanced for weight, and the gyroscopes are on one side and the motor is on the other side. So if I remove the gyroscope, the weights will no longer balance, and the dish will begin to tilt and to lean, and it will become less accurate. So removing them will require that I weigh them exactly, and then mount the same weight at the same position from the center of rotation. And that's a lot of work. So to answer the question of what the gyroscopes are doing, they are very crucial, very important dead weight. Someone. I think this, and then one more question, and then we'll let the next talk begin.
Have you considered using it for mapping dead satellites, junk in space, to be cleared out? You pick out the working ones, and those that don't work, mark them as junk.
I did think about turning the 200-watt transmitter into 200 watts of radar. Then I thought better of it. Again, I don't want to... I'm a bit shy to transmit. Transmitting will piss people off. It's kind of like how you can do whatever hacking you want on your own computer without caring that much. But as soon as you start hitting a server that someone else controls, it becomes a big deal. At the moment, I'm only receiving, so I don't have to worry about breaking anything. Can you imagine how guilty you would feel if you started playing with a satellite and you broke it? Especially something important, all you really wanted was a picture out of the satellite. You connected to it, you thought you were turning something on, and then something short-circuited and the whole thing fell out of the sky. I'd feel bad about that. Maybe you wouldn't. Frank wouldn't. Okay, last question?
Yeah, as a former TV broadcast engineer, I would just want to say you did great stuff. And I just wondered if you ever tried to decode any of the digital data you received.
I have. But at the moment, I've been receiving the simple stuff. So a lot of these satellites transmit Morse code beacon so that they can be found within the sky. Those are very easy to receive. You just do the plot and you'll actually visually see the Morse code come through. I've also reverse engineered the global star format, but the transmitter for that is just at the top range of what I can receive. So I can see the signal, but I can only interpret it on the uplink right now. I need better recordings to do the downlink. So at the end of the month, I'm going back to Tennessee, and I'm adding a 20 megahertz wide HAC-RF radio, which goes up to 6 gigahertz. And I'm going to experiment with replacing the antenna to try and move the frequency from a center at 1.5 gigahertz to a center at 2.1 gigahertz, which will get me very clear receivings of reception of the global star network. Then I will be able to receive asset tracking, because people use this to track trucks and trains and ships. So I will be able to draw a map of where they are by grabbing the GPS coordinates out of the sky. I won't know what is at that location, but I will know where it is. Cool. All right. Thank you kindly for your time and attention.